Thank you very much. Can you hear me in the back? My voice is not carrying very well. I came to IMPA the first time before most of you were born. And this is 1972. It may have been 1872 for all that I... So IMPA wasn't up here, it was down there in Rua Luis de Camões 68. And this place is, so I always consider this place at home, as home. Right? So come back here. My talk today is sort of related to the couple of talks that Luis and Carlos gave yesterday, which is a good chance to thank George for putting all of this together. If you're actually filming me, I should have taken a shower before I came here, but I didn't know that this was going to happen. So this is all, 99% is about classical probability. At the very end, I have a couple of words to say about quantum possibilities of doing something. And I'm going to assume different people have different backgrounds. I'm not going to assume that you know anything in particular. At some point, everything is going to turn into something that is, I think, rather straightforward. But the history of this in itself is rather interesting. So the talks yesterday had something to do with the quantum world. That's from whatever, around the 1900s on. But I'm much older than all that. So this is where I take my origin. I was a student around that time. And this was one of the many proposals that people had for producing a machine that would be able to produce work. I'm not going to define these terms. And actually do this without spending any energy. And if you look carefully, there is water, I presume, that comes in here, and this makes this fellow rotate. And then there are some levers and different things, and there is more water or caipirinha or something coming on that side. So these machines were made up of different pieces, and this is part of what is going to show up in the talk. Now, much later on, by the end of the, okay, I just said that this proposed machine, this one and many other ones, equally hopeless, were made of smaller pieces combined properly. And the idea of combining two things to get a larger one with the same purpose is sort of the main theme in this talk. By the end of the 1800s and beginning of the 1900s, there were actual papers. I mean, there are many, many more. I just picked a few references where people were analyzing the possibility of doing some of these things. Smoluchowski was one of the heroes of Mark Katz. He's a Polish math physicist who came up with his own theory of Brownian motion, among other things. Now, this topic, there are lots of papers in between here. This is not a paper. This is one of the lecture notes, lecture number 46 in volume 1 of Richard Feynman, written about, I think the year is correct. This is a course in physics, and at some point he talks indirectly about this perpetual motion machine. What he's really talking about is taking two machines that do something, putting them together, and getting more for the same price. Okay? And there is a very simple argument. We'll talk a little bit about this, actually in a caricature of this. And then there are these two Spanish physicists, Juan Manuel Parrondo, which is the one that I took for the title of the talk, and this man, Espanol, I never met him. And they wrote a paper several years later criticizing something that Feynman had argued in this particular lecture. If you want to find the lecture, the word ratchet is in the title of the lecture. Okay? And this would have stayed as a very inaccessible piece of thermodynamics. All of this has to do with thermodynamics. Hopefully some of you have suffered through that. It is, in my view, the most difficult piece of all of physics. I mean, quantum mechanics is for children. thermodynamics is impossible to understand. But we got lucky. Parrondo himself started talking to different people, and fairly soon, this may be the first paper, but there may be something in between. These two guys who are sort of computer science, statistics, whatever you want to call them, in Australia, took away, as it says here, all the thermodynamics in this. Here, see, yesterday I was criticizing Luis for misspelling Feynman, and his vengeance is here. He had too many ends, I have too few ends. Okay. So they managed to convert these ideas into a game that exhibits something that people should find, I think, rather surprising. Okay? So that's what we're going to be talking about. I mean, please interrupt me or leave the room or do whatever you want. Just feel free. You don't have to. You're not being filmed, so you can do whatever you want. Okay? So I'll talk about games. A game, each one of the games that appear here are a player against a casino, and they are tossing, the player is tossing a coin over and over. The coins that will appear here will be unfair coins. Okay? At each toss of the coin, the player either wins $1 or loses $1. And we say that a game is losing if, when you look at the total fortune of the player, that is, you add a +1 if you win, you take a -1 if you lose, you do the sum of that. If the total fortune as a function of time gets, on average, more and more negative, you say that this is a losing game. Nothing really shocking about that. At some point, when I get to the math, we will need the number of times that you're tossing to be infinity. But in practice, if you do this 10 times, is quite okay. Okay? So for a losing game, pictures like this will appear several times. Here is time. Time is actually discrete, but I don't know how I did this by hand, so it looks continuous. The fortune of the player could be positive or negative. I didn't know how to do a line that way. My abilities are very limited. So you start at 0, the fortune of the play, and presumably the player has been winning for a while, then it's losing for a while, then who knows what is happening here. But eventually you see this trend going down there, okay? And each one of these games is going to be a probabilistic thing. So when I say it's a losing game, even if you're playing against the biased coin against you, you may still win all the time, but that's very, very unlikely, okay? So now I'm going to describe these two games in some detail. The games are actually very simple. Game 1, the player against the casino using an unfair coin, and the probability that our player has of winning at each toss is always exactly the same coin, is some number that I call P0, and I want this to be a coin biased against the player. So I'll take it to be 1/2 minus mu, and mu will be determined later, small enough. But clearly, this is, you don't need any math to know what's going to happen. Eventually, you're going to be wiped out, okay? That's all right. So initially, the fortune of our player is 0, and at time n is the connection of these pluses and minuses, okay? And this is a losing game, and you don't need anything for that. Is that okay? No? Second game, and this is the last game. So the first game is a caricature of that first engine that Feynman was talking about, and game 2 is going to be a caricature of the second engine, and then we need a way of combining them, okay? But we're not going back to thermodynamics at all. So now in game 2, this game 2 has nothing to do with game 1. So it's a good idea to think that you play some game on some days, and you play this other game on different days. It's again the same player playing against the casino, but at each turn, she chooses either one coin or another coin. There are now 2 coins, and you have to decide which one you're going to use. And there is a rule that says which one you're going to toss is a function of the fortune of the player at that given moment. So initially the fortune was 0, then the fortune in the next moment is going to be 1 or minus 1. Then after that it gets messier, because it could be 2, but it could be 0, it could be minus 2, and it starts branching. So we'll get into this. So the rule that I will mention a couple of times is given here for the first time. If the fortune of the player, I should say, is a multiple of 3, like initially it was 0, an integer multiple of 3 I should have said, she uses one coin, otherwise she uses the other coin. Each one of these coins gives our player a certain probability of winning, and now I'll give you some details, okay? Now, multiple of 3 means that you belong to this set here, 0, 3, 6, imagine all of them here. Then she uses one coin such that the probability of our player winning is a quantity that I call P1. If the fortune is not a multiple of 3, then she uses the other coin, which has probability of winning for the player equal to P2. And if you look, we're going to use these values here, okay? You can assume that these are general numbers, but it's important if you want to see something surprising to use these values. And this is the same mu as before, and we will pick it later. How I pick it is to be decided. So clearly, in this case, this is clear. When she's going to use this coin, the casino is going to win with good probability, whereas if you have to choose the other coin, she is going to win. Okay? But there is a fixed rule for deciding which of the two you're going to be using. Okay, and there is only one question here. What's the probability that our player will win at time n, when n is 0, 1, 2, and you want to see what is happening eventually. And we're going to have a losing game if these numbers turn out to be less than a half for large n, an asymptotically losing game. Don't worry about asymptotics. N equal to 10 is good enough, and thereon. And the player will have a winning game if these numbers go to some number larger than a half. Okay? So for lack of names, I'm calling the probability of this winning thing, I call it W sub n. So let's compute the first few values of W. The first few can be done very, very easily. I mean, there is nothing really deep here. It's a question of choice. What do you call deep? It is very simple. That may be deep too. Who knows? So at time 0, the fortune is 0. So since 0 is a multiple of 3, we're going to use that coin, which this probability, and this is trivial to compute. After that, the fortune is 1 or minus 1. Now, since neither these two values is a multiple of 3, then the probability of winning the second time is necessarily P2. And then after that, the fortune gets more complicated. What I said before, could go up to 2, or down to 0, or down to minus 2. And, well, it's not so easy to give a formula. Of course, one can give a formula for W2, but when you start getting n to be large, this becomes a little mess. All right? So we need to find, we have to abandon this very primitive way of computing the things and do some math or whatever you want to call it. Okay? At some point, the Markov chain will appear. The Markov chain is almost there now. So that's what I just said before. It will be useful. You may try to do it in other ways. I'm not saying this is the only way to analyze this. Okay? We're still trying to compute the WNs. That's what we really want to do. There is nothing else to compute, which in the language of Feynman would be either the machine produces work or doesn't produce work. But I'm jumping over the analogy. So we will find it useful to compute the probabilities that at a given time the fortune is in this set or in the complement, but the complement I'm going to break into two pieces. So these are all numbers congruent to 1 mod 3, and these are all the numbers congruent to 2 mod 3. Okay? you may be tempted to set up, as I will do in a moment, a two-state Markov chain consisting of two states. Just either your fortune is here or your fortune is in the union of these two things. I don't know how to make that work. Somebody may be able to do it. I will do it this way. And then once a person, the player, wins or loses, her fortune cannot stay in the same class, right? You either increase by 1 or decrease by 1. So if you are at 6, you can either go to 7, which means you go down there, or you can go to 5, but you don't stay in the same class, okay? All right, so these names will appear often. I call this the probability of being in the first class at time n. This is an auxiliary thing that I'm introducing to be able to compute what I really need to compute. This is the probability of being in the second set, the numbers that are congruent to 1 mod 3. And this is the probability of being in the third set, numbers congruent to 2 mod 3. And now I'm using here the Markov property of the thing, the way the game has no memory. There was the question about memory yesterday. The probability of winning is either you are in the first class, clearly these three numbers are greater or equal than 0 and are up to 1, okay? Because this is an exhaustive listing of all the places where the fortune could be. Either you are there and then the rules say you have to use the first coin with probability P1, or you are in the second class and then you use the coin P2, or you are in the third class and you use the same coin P2. You can make the game more general, putting some P3. We don't need to do that. And the question is, how am I going to compute these quantities? Once I have these guys, I'm finished. I just use that formula there. So this formula will reappear in different instances, but the important thing is how do I compute that? If this is not easier to compute the WNs, what's the point of introducing them? All right? As I said, we have reduced the problem to computing these guys. So here comes the first place where Parrondo and Español were criticizing Feynman. And we are jumping over lots of things here. Feynman wasn't playing this game. Feynman was probably playing the bongos somewhere in Rio. Certainly more fun. He doesn't know how to compute these numbers, but he thinks, and I'm abusing Feynman, but I'm sure he wouldn't mind. These three sets have different sizes. Do they? No, in fact, they have the same size. They're infinite sets, so the language is a little bit dangerous here. So what probabilities would you assign to these things? Well, why don't you say, with Feynman, that we should put 1/3, 1/3, and 1/3. Let's say that for every n, those are the probabilities, okay? And then, okay, we believe in Feynman because he's Feynman, and we are not. So back to the formula. This is the first value times P1. Then there was a 1/3 times P2 and 1/3 times P2. You add up, you do the algebra. Now I'm using the values that I gave you. Hopefully the algebra is correct. And you get 1/2 plus 1/30 minus mu. Okay? This is if Feynman was correct. Now clearly if mu is small enough, this is larger than 1/2, and we should have a winning game, because the probability of winning at time n is in fact this constant, and it can be made bigger than 1/2 just by choosing mu small enough. So let's go and play. When you play, this is what you find, that no matter what Feynman told you, this is actually a losing game, okay? That's the way, just do it. Or, as we will see later, we may think that even Feynman can make simplifying mistakes. And so this is the model. Don't follow Dick all the time. So we're going to do this more carefully. Now, for the first time, I'm going to do some simple math, but I think, the really surprising part comes much later, but we have to do this. consider a Markov chain with 3 states. Each one of these is the congruency classes that I talked about earlier. And I'm going to call the first class 0. These are all the numbers congruent to 0 mod 3, all the numbers congruent to 1 or 2 mod 3. And now there is a very simple transition probability matrix. And the way that I write things, the matrix will have the sum of the columns will be 1. The usual game with the Markov chain, you have to make a choice. Okay, so I'm going to write that matrix in a moment. I mean, this is, I'm not sure if this is useful or not. Just as a warm-up, if I was trying to analyze game number 1 using this machinery, which is really stupid because nobody needs to analyze that in any pedantic way, the matrix will look like this because there is only one coin. And you can go, if you're in this class, the probability of winning is P0. Okay, so this is class number 0. The probability of losing, which is to go to class number 2, because you're going to go to -1, which is congruent with 2 mod 3. I mean, they are in the same class, is the 1 minus P0. So this is the matrix you would have. We're not going to see this matrix for a long, long time. But this is the matrix that you would write down if you were analyzing game number 1, which is rather silly. But keep it around. So for game number 2, the matrix is the one that I have here. If I am in class 0, the probability of going to class 1 is P1 because I used that coin. The probability of going to class 2 is 1 minus P1. Notice all the zeros in the center. That means that you cannot stay in the same state because that's the way it is. So this, and the fact that here the P2 appears both here and there is because I have just 2 coins. You could make it more complicated. Okay? So I will come to this matrix in a moment. So now I need a little bit of notation, and here is the only thing that is non-trivial. If you had a general Markov chain with three states, and this is the matrix P, I'm going to denote with this notation pi super n a column vector with the 3 components. These are the numbers that I was looking at. The only place where you can call this anything you want, math, physics, intuition, human experience, whatever you want to call it. The point is that although you don't know what these vectors, this is a vector with 3 components. The important relation is that they evolve according to this evolution here. And for this, just write down the product matrix. I mean, matrices are a great invention, so are vectors, and so is the multiply. And if you don't take me seriously, most of you must know the story that Heisenberg, when he wrote down a mathematical formulation of quantum mechanics, thought of a good idea of putting together these numbers in a rectangle or in a square, and then went to Born and said, look what I did. And Born said, congratulations, you have reinvented matrix analysis. Heisenberg didn't know that matrices existed as an object, okay? And much less matrix multiply. But this is essentially, this is the crucial thing. So we have that. So now we are going to pray. I pray, I'm hoping that I'm in such a situation as we are in this case here, that this is, I read it yesterday and it was the English here is all wrong. But I'm going to assume that n is very large, and I'm going to hope that this vector, which is moving with n, actually converges to a limit. In our case, there is a theorem, Parrondo, Frobenius, some name like that, that says that this actually happens. So this sequence, no matter where you start, has a limit. The limit is unique, okay? But if you take the previous relation very seriously, and you're sitting way, way back there, and n is 10 to the 23, well, this is also 10 to the 23, so, or pass to the limit if you want to be pedantic, this must be satisfied. So all of a sudden, we have a way of computing pi, or the limiting value of pi, because it's an eigenvector of p with eigenvalue 1. That's what it says here. Now, suppose we are so lucky that this matrix being stochastic and the name is irreducible, that's some definition, happens to have a unique eigenvector with eigenvalue 1. Okay? When I say unique, I mean up to scaling, of course, but the sum of the three components has to be 1. So I claim that under certain conditions on the transition matrix, namely being stochastic and being irreducible, okay? Those are not necessary, but they are certainly sufficient conditions. You can prove, this is Parrondo Frobenius or some other name, I don't know how it is called these days, that we can then, as soon as we can do some linear algebra, we're done, okay, to find the pi. So let's do that. Well, if you want to be silly, you can go and use this machinery for game 1, but I don't want to do. Here is, you can compute, and you get that Wn is, this is another misspelling, anyway, shouldn't do the transparencies on the plane. The Wn is always P0. This is all very silly. This was the first game. You don't need any of that. Now, just for your linear algebra class, George, I show you here, suppose you had 3 different coins, okay? You can show that the normalized eigenvector with eigenvalue 1, normalized meaning the sum of the 3 components is equal to 1, and this is horrible, I have changed the notation, okay? But in terms of the P1, P2, and P3, eventually we'll take P3 to be equal to P2. These are the components. You can check. When S is the normalizing factor, okay? S is given by some expression there. And if you wanted to compute the corresponding vector, so you don't have to listen to Feynman and say 1/3, 1/3, and 1/3, the correct values are given there, okay? And what happens next? So now I can ignore Feynman, and we compute the Wn at least for large values of n, computing the limiting value, okay? So here are the names that I have given the limiting values. There is no more any n. You stick it in the formula there. You should have taught me more tech, so I know how to cut, but I don't know how to do that. Anyway, now you use for the first time these values. Up to now, this was totally general. You use the values that I had promised before, and you get for large values of n, the Wn, okay? Remember the formula for Wn had to do with computing these pi's. Okay, here it is. It's that formula. It's not that far. You have to plug everything. You do the algebra, and I'm going to do a Taylor expansion in mu here, okay? It's a nice rational function. You can do that, and you get the following thing. It's 1/2, thanks God there is a minus sign here, minus this positive coefficient times mu plus higher order terms. So if I take mu tiny enough so that I can neglect, brutally speaking, all the higher order terms, this number is smaller than 1/2. So as a function of the mu, this has the value 1/2, but when mu gets a little bit positive in some small region, this quantity is less than 1/2. And what have we learned? We've learned that the game 2 is a losing game for the player, which is not a surprise at all. That's what the experiment showed. So all that we did was to cook up a way to compute correctly the asymptotic value of Wn, which if you had followed Feynman advice, didn't want to do all this nonsense with 3×3 matrices, he just said 1/3, 1/3, 1/3. Well, the conclusion that was a mistake that actually had consequences, because it predicted that this game was supposed to be a winning game, where in fact it was a losing game. And here we have checked. Okay, where are we now? I have, what, 4 more hours to go?
Yes.
Very good. Thank you. So let me, in the title of the talk, there was the word paradox, and I have not mentioned the word paradox yet, and that's the point. All that we have, and we have seen all the math that there is to see. So the math that gets involved is actually very basic. I think it's deep, but it's still basic. All that we have is a good way to compute for large n the values of these for each one of the games. In one case, it was this P0 that was by construction less than a half. In the second case is this number that I just computed a moment ago, which if mu is small, is less than a half. So they are both losing games, and we're perfectly happy. Okay? So these are the two machines. Suppose these two machines, now in the language that Feynman might be using, do something or other. Let's say both of them fail to produce energy, or both of them produce work. I shouldn't use the word energy. Work. Okay? So this is where a new theme enters. I want to combine these two machines, or combine these games, game 1 and 2, and I'm going to invent a new game, which is actually just made up of these two other games. Okay? There are different ways of doing this, and I have to remember that for later. But here, the computation that I have done here is just one of the ways. So I bring a neutral observer. So poor Luis sitting there, desperately trying to think of something else. We will use him all the time. So we're going to be combining these two games, all right? And we'll call the new game Game 3. Okay, so initially, the player now is going to play Game 3, and these are the rules. The fortune is initially at 0, but she doesn't know if she has to play Game 1 or Game 2. Game 1 has its own rules, namely no rules at all, just use the coin P0 all the time. Game 2 has these rules that are slightly more complicated. Look at your fortune and decide which of the two coins to use. So the observer brings a fair coin, 50-50. This doesn't have to be 50-50, but it is in the computation that I have made here. Depending on the outcome of this toss, our player will play Game 1 or Game 2. So this is the rule. If it comes out heads, probability half, you play Game 1 with its rules. If it comes out tails, you play Game 2 with its rules. That's at the end. Then after this, the observer cannot leave the room. You're stuck there forever, Luis. You have to toss again and report if you have a head or a tail. Depending on that, the player plays Game 1 or Game 2, and you keep on going. Okay? This is a good moment to say, I'm sure if we do this a few times, Luis will stop coming. So then we'll do the following. We can even do without Luis for this game. We cannot do without Luis for other things. But we'll say, OK, why don't you forget about this randomizing the choice? Why don't you play Game 1, followed by 2, followed by 1, followed by 2, followed by 1, followed by 2. OK? So this is another way, and the computation could have done in that way. What I want is to make sure that, on average, half of the time you're playing Game 1, and half of the time you're playing Game 2. That was certainly the case here with this fair coin. All right? I'll come back to that later. So I claim that from what we learned before, you have to do the same thing again. It is the same Markov chain, but now there is a slightly different transition probability matrix. See, if you notice, what I've done to get this matrix is take 1/2 of one transition matrix plus 1/2 of the other. Because, say, if you are in state 0, with probability 1/2, you're going to be playing Game 1, which has P0 for the chance of winning, or Game 2, which has probability P1. So this is the matrix to analyze. It's totally simple. If I didn't have a fair coin, I would not have these 1/2s here. I would have whatever, 0.48 and 0.52, and the algebra gets better, worse, and the matrix gets bigger. But remember, we have learned, because we don't trust, we're not going to go and ask Feynman again, although I'm sure he would have some guess. We have a formula, so I say this way of combining two games corresponds to his way of putting together two machines. Okay? So what Feynman did, and this was the article of Parrondo. Parrondo said the following. See, let's go back to Feynman. When computing the work produced by this combination, in our case, the probability of our player winning, Feynman argues that a combination of two machines that produce work is a new machine that produces work. I mean, you have to be extremely obscene or dirty-minded or twisted in other way not to believe that thing. So nothing too shocking. Well, till you run into someone like Parrondo, an Espanol, who read carefully, and they were not convinced by the argument. As I told you, thermodynamics is so confusing that even Feynman can get into troubles. So we're going to do the algebra. I'm going to return to this eigenvector now for the new matrix. Sometimes it's called the Perron-Frobenius eigenvector. You compute as before, you do a Taylor expansion, and you find out that for large n, see, the formula was fixed in there once and for all. So you apply that, and this is the computation. I do not advise that you do this by hand. I mean, this was done using maxima in my case, but you are young and you can use whatever you want. Maxima is what the dinosaurs used. And if you, now I notice that if I take the difference between 27 and 18 is 9, so I write this number in this silly way and copy the other one. You notice now, and this is positive, thanks God, that if mu, remember the mu, we just had to pick it small. I'm going to pick now the mu small enough that this is now, this number is larger than a half. That's the way it goes. And you conclude that this fair combination of two losing games is a winning game. Okay? This is the paradox. I mean, Parrondo paradox is not that Feynman was wrong in putting the 1/3. That's just a silly point. The point is that any sensible person will assume that if you combine two losing things, you get a losing one, and, well, you have to be careful. Clearly, I'm not saying at all, I've been accused of lying. Sometimes that is true, I am lying, but not this time. I'm not saying that if you combine any two losing games, you get a winning game, or else the world wouldn't be, we wouldn't be around, okay? I'm saying that if you pick things, so this is what happens for game 3, and my advice, no, if you're teaching young students, don't tell them about eigenvectors and eigenvalues, just play the game, and you will see. It's very difficult to simulate coins that have those probabilities, and the numbers are chosen carefully. They are not the only numbers. I mentioned before that the same phenomenon can be seen if you alternate games 1 and 2 in a purely deterministic fashion, and I'm almost done. So here is the challenge. I'm a finite number of slides from the end for large finite numbers. The big challenge is to explore this phenomenon when you replace classical walks by what are called unitary quantum walks. Never mind what that is. But if you were present at Luis's lecture yesterday, and Carlos, you know all of this, or what are called open quantum walks. And a number of things may have to be revised. It may be the case that certainly for quantum walks, very, very quantum ones, the unitary ones, the notion of stopping to check what is the value of my fortune cannot be implemented, because that in terms per term, talking about the monitoring that we had yesterday and so on. So I'm not saying just do a straightforward extension of this. I'm simply saying play with this and see what happens. Let me come back to this. So there is a paper that I wrote with Michael Pejek, a PhD student of mine in Berkeley, where we don't do the same thing of Parrondo. There is something that we call maximal Parrondo. Small difference, but it's a similar idea. Combining two things and getting surprises, both in the classical and the quantum case. But this is not necessarily what I have in mind. So let me just talk, because this is the slide I want to see. Yeah, so this is my last slide. This is something that I was doing a couple of days ago. Among the unitary quantum walks, the ones, remember, Luis talked yesterday about Aharonov The game that the coin walk that he proposed is what is called the Hadamard walk, and that is an example of a coined walk. A coined walk, I don't want to write too many things on the blackboard, I could if somebody wants. They consist of two things. You have a unitary matrix 2 by 2, which is called the coin, and there is a shift. See, if you are spin up sitting in place 7, you can go to spin up in place 8, or you can reverse the spin and go to place 6. If you were at place 7 with spin down, you can go either to the right, which is 8, with the spin down, or to the left with the spin down. The amplitudes of these transitions is governed by a certain unitary matrix. Okay, so there are two things. A unitary matrix that tells you the amplitude of certain transitions, and then this so-called shift. So I have an example which I'm not happy with it, but I will tell you what I have. I can find two coins, so that when you consider each one of these coins, started at an initial state psi. If you remember a picture that both Luis and Carlos showed you yesterday, the analog of the Gaussian, this is all on the integers, and both of them showed a picture that looked like this, more or less, with heavy tails. Most of the distribution is at the end points, okay? But that was because the initial state had been chosen very, very, very carefully to make sure that things are symmetric. So I choose a state where for the first coin and for the second one, the graph, I should have put that on will look like this. So I would say, so this replaces this graph, okay? This is asymptotic distribution of the sides, the positions, ignoring the spin, where I have started with such an initial state that I'm not unbiased. So I would say, in this case, this is a losing game, because the left-hand side is favored over the other one. So that's the C1. Then I do another game where, once again, I have the same shape. And now, so these are two losing games. I want to combine them. Well, here, I didn't have time to do this carefully, so this is what I did. I'm cheating. What I do is I multiply the two unitary matrices and then do the shift. I mean, the correct way to do, even if you were do, so here I'm avoiding probability or anything like that. I'm simply saying I'm going to run this coined walk and then that coined walk, and then this coined walk and that coined walk. Well, that is not exactly what I do when I write the thing here, okay? But it's a little bit similar, okay? And what I get by doing some algebra and then simulations and so on, I get, for the same initial state in all the three cases, I get something that looks that way. So I would say this is not what I should be doing. I realize that. I'm composing them in a funny way, okay? And this is not what I should be doing. I take that. And then the real thing to do, there is much more exploring to do. I mean, this is all very simple to analyze, whereas this other story is just very hard to penetrate. So this is one contribution to my being here, having found an example. It's not entirely trivial. You have to find the initial state carefully, and you have to find these coins carefully, but you see some of that. Now, the literature, this is a question for Carlos and maybe Luis too. This man Mayer, David Mayer, is supposed to have shown, although I'm not sure what the real statement is, that you cannot have Parrondo in the quantum case. I don't know. I mean, I understand my computations. I don't know what other people claim to have done. It may be that one has to get away from coined walks. There is, I have to say something about CMV matrices. You can forget about the G, that's me. CMV stands for Cantero, Moral, and Velázquez. Luis Velázquez is sitting there. They did, I would say, exactly what Jacobi did for symmetric self-adjoint matrices, they did it for unitary matrices. If you want to have an evolution given, say, a birth and death process, which is by definition something that has only 3 lines, okay? That can always be symmetrized, and then there is a whole theory, orthogonal polynomials, all that. But the basic fact of writing this matrix in a nice way, or the theorem, well, there are theorems, you guys know more about this. Stone, what was his first name? Marshall. Marshall Stone wrote a paper proving that in a Hilbert space, if you have a self-adjoint operator, there is always an orthonormal basis, so that the operator can be written as a tridiagonal matrix. Okay? It may be very difficult to implement the orthogonal thing, but that's your problem. You can ask what happens if you replace orthogonal. I'm sorry, I wanted to say, I said self-adjoint, I hope. For a self-adjoint, that's Marshall Stone's theorem around, I don't know, 1930, something like that. I'm sure that any such date is wrong. Somebody must have done it earlier. That's okay. But you can ask what happens if I replace self-adjoint by unitary. So replace the real line by the unit circle. You may be pleased to know that there is such a construction. He's responsible for it. So if you don't like it, you should blame him, not me. There is a so-called CMV form of an arbitrary unitary matrix that, if you're sitting very, very far, looks like a tridiagonal. The blocks are a little bit larger. It's actually 5 diagonals, zeros. I think that people should be using those matrices for all sort of other things. The fact that it's unitary, that they are unitary, made me think that maybe for quantum walks they were a natural tool. And okay, coming back to this, even if Meyer proved that you cannot have Parrondo, which I don't know if that's true or not, I never really read his stuff. It is plausible, I hope, this would be nice, to find 2 CMVs so that when you alternate them, there is no longer a CMV. Even the product of 2 of them is no longer, because you keep making the band bigger already with 1 step, that you could have the combination of 2 guys biased one way turning out to be biased the other way. The difficulty there is that for coined walks, there are limit theorems that tell you these are the things that happen. For CMV ones, much work needs to be done, and that's my last word. Thank you. Okay, thank you for your patience. Two by two is the basic case of spin up and spin down. But what I'm not happy, what is the word? Luis will help us. We have this statement, these Japanese guys, the ones doing topological phase, they take 2 coined walks, they put them together in a certain way, and we claim that that's just a CMV. Split step. On the taxi we were Uber, I'm sorry, not taxi. We were talking about staggered. He says that somebody talked about some staggered walks that are more general. I bet you coined that.
I'm not claiming it's more general.
No?
Related.
Okay, related. Okay. So people use things called split coined walks. Am I correct? Split step. And if you do, so you put 2 of them together in a certain way, I have to go and look. And at one point we convinced ourselves that this is nothing but a CMV, correct? So that's a nice way of describing how do CMV matrices in the quantum case go beyond coined walks. Maybe that's what it is.
In one dimension, it's true that every quantum walk that has a finite interaction and a finite size. I'm talking about the unitary with the band structure.
Yeah.
Every such a unitary can be obtained as a composition of sheets and typical coins. So TMB is a bit more general
No.
in some sense.
No, but if you were to just, I mean, my statement I think is true. That it, no,
That you can,
that if you
that you can use
the
a
split
basic
step, yeah.
so that you can get the TMB. And in such sense, it's the most complicated one.
That's right.
You cannot get anything.
Yeah.
because
If I want you to remember something, is my view, and this is not my work, so I can say whatever I want. CMV matrices should be used for everything, or for lots of other things that people haven't thought about using them. And the connection with beautiful 1910, 1920, 40, and so on, classical analysis is all ready to be used. That's my statement. You can
that's
agree?
true, I should do a patent.
You should get a patent. Well,
I don't think you can read this video, so.
Alberto,
well,
I have a question.
Mhm.
Okay, actually, two questions. I was flipping a coin between the two questions, but let me try one question. How about the taking the limit as the time steps goes to 0? Can you continue on this game and take appropriate limits where you guarantee for some games that losing strategy, losing games will give you winning games? Or can you patch the limits?
okay, amazing. This is a question that I can answer. I was going to say I certainly haven't. No, I haven't done that. But there is a man whose name will come back in a moment. He was a student in Berkeley with Hans Levy, and he was in Carnegie Mellon. And I have the face here, but I can give you. Yeah, the point is, you don't need to pass to any limit. The phenomenon has been done purely at the continuous level by this man whose face I have. This is a good problem for Google. How do I convey an image or a smell or something? Anyway, he doesn't smell.
Deep learning.
No, that has been done, and I'm embarrassed. I don't remember the name of the person.
This
But without passing to the limit, you
Before
don't
my
need.
second question, let me throw a
Mhm.
coin here. Anyone would like to ask another question? But I have another question as well. So, okay, the other question is, suppose you had a strategist playing
Mhm.
in the mid of the two games. Has this been analyzed? Like, for example, someone's taking a decision, and instead of just tossing the coin, you would be taking some kind of preventive measure based on the past, but without knowing what would be the second step in the. You know, you had
Yeah.
the previous information.
Yeah.
You threw. So you had a coin, the first
Mhm.
coin thrown,
Mhm.
and now you are going to make a decision so
Mhm.
as to what would happen in the second. Like, you know, these games where you have 3 people and
Sure.
someone turns to you and says, no, there is no one there. Do you want to change or not?
Yeah. No, that I certainly do not know. My advice is write to Juan Manuel Parrondo, who is a very nice guy. He used to run, see, in Scientific American, in Spanish, there is such a thing, and for many years he was the editor. He was the Martin Gardner, if you know what I mean, of that thing. And he has, I mean, I assume that if somebody were to do something like that, may have done it already, they would have talked to him if they had any smarts. So he may know. I just don't know. I find this is such a elementary thing. See, what you are describing is much more sophisticated, I think.
It's a strategist game.
Strategy. This is just, and you have this phenomenon. I would find it surprising that you do not have those things, and some people must have. I just don't know, but that would be, yeah. The point that don't come out with the thought that every 2 losing games combine into a winning game, because then you're going to lose even further, right? The numbers.
You can get a given strategy in order to get a losing game at the game 3. That's trivial.
Yeah. But once you get a
Let me.
winning game.
You were no. Okay. Let me tell you what we do here. Hopefully, this is small enough that you cannot read it. But that's why we call it maximal. We prove. So maybe I should have read my paper. Yeah. No, this is not exactly your answer, but what is proved here. I'll just talk of the classical case. Okay. You give me an epsilon, as small as you want, positive. We will construct two games. They are not the ones that Parrondo was using. We will construct two games given the epsilon, and they will have the following features. The probability of you winning in the long run in either one of them is less than epsilon. So they are badly, maximally losing in some sense. And yet, when you combine them in a certain way with a fair coin, if I remember right, then the probability of you winning is larger than 1 minus epsilon. This is pushing it all the way to the end. But look, the real piece of math is the following. What would make all of these Parrondo things go away? The following theorem, which fortunately is not true. Take two matrices. Think of them as the transition probability matrices that I had before for game 1 and game 2. Each one of them has its own Perron-Frobenius vector. This is a unique thing up to normalization, positive component. Now take a convex combination of the two matrices. I put 1/2 and 1/2, but you can put whatever, 1/4 and 3/4. You may think that the Perron-Frobenius of the convex combination is the convex combination of the two individual Perron-Frobenius. If that were true, then no Parrondo. Because that is not true, you have to fool around. So, incidentally, the Perron-Frobenius is not, I was told by my friend Craig Evans, who only lies on Tuesdays, that there is a nonlinear version of all of that. And I even have a paper that I found. I mean, it would be nice to find, say, nonlinear versions of these. I mean, the evolution is not necessarily now going to be given by iterating a certain linear transformation.
Because the infinite dimensional version.
Well, for me, 3 is enough. 2 or 3 is my size. I barely fit in dimension 3, so I could benefit from infinite. Yeah, there is all of that. So, no, my feeling is that, say, look at the way that math develops, or some pieces of math. Feynman did this. Nobody would have read the lecture notes of Feynman carefully, trying to find mistakes, unless this guy was Feynman. Very lucky that Parrondo did that. Very lucky that he then talked to these guys that are not in thermodynamics, and they broke the whole thing open, and now we're all free to play. So I'm sure there are many different versions. But I think the person that you should, I mean, Juan Parrondo is a young man, he's extremely interesting, he's very open, and he's in, whatever, Complutense in Madrid, I think. Okay?
There are no more questions. Let's thank Alberto again. Thank
Good.
you very much.